Okay, on the hour here, I think we're going to get going. My name is Becca. I'm with AGU Media Relations Office, and I will be helping to moderate this press briefing. The topic of this press briefing is NASA's 2022 Earth Science launches, and we will start with a presentation from each of the panelists where they will describe 4 upcoming Earth observing missions that will be launching next year, and then we'll open it up to questions from reporters. The briefing will end on the hour or when there are no more questions from the reporters, whichever comes first. And reporters who are on site in New Orleans are welcome to meet with on-site panelists in the quiet room R05 following the event. Reporters, because this is a Zoom webinar, you will not be able to turn on your video or microphone. So if you would like to ask a question, please type your full name and affiliation into the Q&A box, not the chat box. And we will request that you unmute yourself in order to ask your question, and we'll do so in the order that the requests were received. If you'd prefer, you can also just type your question into that Q&A box along with your name and affiliation, and we'll pose it to the panel on your behalf. You can write in your question at any time, but we won't ask them until the panelists have finished with their presentations during the Q&A session. And it would be helpful if everybody, all the journalists in attendance, please take a moment and check that your name is correct so that we can find you easily in the participant list. Slides and any other materials from this briefing will be posted to the Press Information Exchange on AGU Connect, and we'll drop a link to that in the chat. This event is being recorded and it will be posted to AGU's YouTube channel as well as linked to in the Press Information Exchange on AGU Connect as well. Should any technical issues arise, like if Zoom webinar goes down for some reason, we will continue holding this press briefing through a teleconference line. And if that does happen, we will send out an email immediately to all attendees and panelists with instructions on how to get into that teleconference to keep this event going. If you run into any technical issues during this briefing, please do email news@agu.org and we can get you in touch with someone who can help. And with that, I will turn it over to our panelists. So Karen, if you want to take it away.
All right. Hello, everyone. My name is Karen St. Germain, and I'm the Director of Earth Science for NASA. It's terrific to be with you today talking about our upcoming missions. If we go to the next slide, please. So often when people think of NASA, of course, they think of human exploration or planetary science or astrophysics. They might not think of NASA as using the unique vantage point of space to look back at our home planet. But of course, NASA has been studying our home planet for decades now, and it's largely because of NASA satellites that we really do have an understanding of how our climate is changing on Earth. And we know that that change is accelerating as in ways that we haven't seen before. And because of that change, decision makers at every level need information and actionable science, whether it's at the local level, concerned about transportation issues, to sunny day flooding, to agricultural issues and so forth. So on the next chart, please. NASA is, this is a multi-agency, multi-stakeholder enterprise, and NASA has a very unique role for at least 2 reasons. One is that NASA has the only Earth system science program that is end-to-end, from investing in technology to flight missions to funding discovery through research and analysis, to all the way to end user applications that we often build in partnership with other agencies, the private sector or nonprofits. So we're the only agency that has this kind of end-to-end focus on Earth science. But also because NASA builds all of the US assets in civil space. Next chart, please. So today we have a fleet of 23 missions flying, looking back at our Earth. Those are depicted in blue and green on this slide. And those missions that are in orange to gold are missions that are in development or formulation. So we have an enormous fleet looking at the atmosphere, the land, the ice, and the oceans, studying the entire Earth system. And even as we are flying and building these missions today, and in the next few minutes here, you'll hear about 4 that are set to launch this year. We're also looking to the future beyond these missions. So if we go to the next chart, please. As we look even beyond the missions that are flying today or launching tomorrow, and looking toward those systems that are in planning right now, NASA is planning to launch the Earth System Observatory by the end of the decade to meet the needs in future decades. The Earth System Observatory is a fleet of satellite missions that are designed to address the most urgent questions as identified by our National Academy of Science. And the 5 core missions will again look at clouds, convection, and precipitation, in other words, the atmosphere and aerosols. They'll look at the surface of the Earth, both the biology and the deformation and change, as well as what's going on with large-scale mass redistribution, which could be anything from glacial melt to movement of water in underground aquifers. But how we operate this observatory is just as important as what we build. And if you go to the next slide, please. We're also going to augment the core observatory with a series of competed missions that will bring innovation and additional observations to the observatory depicted here. And this will all be a competed layer, which we hope to be able to start this year. And if we just go to my final slide here, beyond what we build is what we then do with the data, and the urgency of the demand for actionable information drives us to do the science with these missions in ways that we never have before, in full partnership with both U.S. government agencies and partners in the commercial sector, as well as international partners. And we're doing this all through open science. The idea there is to put the data, the models, the code, all out into an open ecosystem to lower the barriers to participate in the science with us. We're doing this because we think that will accelerate the pace of discovery, as well as the speed at which we're able to uptake the science and make it useful to decision makers. So we are really excited to talk to you today for the rest of this session about the missions that will be launching just in the next year. They're part of this broader enterprise that is bringing science to bear for decision makers around the country and around the world. Thank you.
Hi, everyone. I am Bill Blackwell. I am the principal investigator of the Tropics mission, which is part of the NASA Earth Venture portfolio. And the objective of Tropics is to measure tropical cyclones with much improved revisit rates, so we can capture the dynamics of the tropical cyclones as they're evolving and intensifying. And the reason we need to do a better job at this is so we can improve the forecasting of the intensification and the tracks of where the hurricanes will go. And that will aid, of course, in disaster management, helping people get out of the way of these very severe storms. So it's a constellation of 6 very small CubeSat satellites that will orbit the Earth and provide revisit rates better than 60 minutes. Next slide, please. So the key observables that we need to measure from space are as follows. So first is the humidity profile. So the amount of moisture in the air as a function of altitude and space around the storm really tells us how the storm might intensify. This warm, moist air is really the engine that drives the storm. So we need to measure that with very high resolution and with very high temporal update. If you click ahead, you'll see that the next observable is temperature. So this is a cross section of the temperature profile through the eye of the hurricane. And an interesting feature here is that there's a warming aloft in the core of the hurricane. And this is highly correlated to the intensity of the hurricane and how it might further intensify. So we need to measure this in 3 dimensions and with high revisit. And if you click ahead once more, precipitation is another thing we need to measure with very high resolution. We need to measure the intensity of the rainfall, the structure of the rain bands. Is there asymmetry, spiraling off from the eye? That tells us things. So these 3 things together, if you click once more, give us a complete picture of the storm that we can measure remotely from these very small satellites in 4 dimensions. Next slide, please. So we've been making these measurements from space for many years. So NOAA flies a fleet of polar orbiting satellites that work very well. They have a number of instruments on board that make exquisite measurements across the electromagnetic spectrum. But these satellites are fairly large and expensive and take a long time to build. And the regret of that is we don't have very many of them. So we need to wait on the order of 4 hours before the next satellite orbits the storm. So that's a pretty large gap. We miss all the dynamics that's happening over that time scale. So a new approach is to augment and complement that network with a series of smaller, more affordable satellites. We can fly more of them. So the Tropics satellites are smaller. They cost on the order of $1 million a piece. And by flying more of them, in the case of Tropics 6, we can get that revisit time down below an hour. And that's where we can really start to say something about how these storms are forming and evolving and intensifying on those rapid timescales. We can also infuse very new technologies to make the best measurements that we can with very high fidelity, very rapidly. Next slide, please. So the Tropics mission is a partnership with a number of partners here with NASA, NOAA, Wisconsin, and others on the science team that are helping us put this together for NASA. These cross-track scanning microwave radiometers measure in 12 channels spanning 90 to 205 gigahertz. With those frequencies, we can measure the temperature and the moisture and the precipitation that we need to inform the variables that I discussed earlier. Now, these are very small satellites. The picture in the lower right gives you a sense of that. They're about a foot long and 10 pounds, about the size of a loaf of bread. But they're very capable instruments that provide very high fidelity measurements that I'll show you here in the next slide. So 6 of these, sorry, not yet, my fault. So 6 of these will launch in the constellation next year, but we've actually launched in June of this year, a 7th satellite that we built. This is our qualification unit that we wanted to put up early in advance of the constellation to give us an opportunity to check out all the aspects of the mission, the ground communication, processing, science, and that has provided some very spectacular imagery that I'll discuss here in a second. So the constellation will launch beginning in March of next year, and Astrospace will be providing the launches for the constellation. So on the next slide, if you go ahead, I just wanted to show you a preview of what we'll get from Tropics based on the Pathfinder that launched in June. So this is an example of imagery at 205 gigahertz of Hurricane Ida as it was impending upon the Gulf Coast. The upper left-hand image shows the storm as it is about to make landfall, but still over the ocean, very intense storm, very clear eye, very clear spiraling rain band out. And 12 hours later, at the middle frame now, we see that the storm is about to make landfall. It's partially made landfall. You can see the blue colors indicate the rain is falling out. And then 12 hours again, in the lower right, you can see that the storm is disorganized after it's made landfall with a lot of rain coming out, but the organized eye has completely dissipated. And this is the kind of dynamics that we're going to try to capture with Tropics. Now, with that, I'll kick it over to Rob Green.
Thank you very much. I'm Rob Green, the PI of the Earth's Surface Mineral Dust Source Investigation. I'd like to quickly tell you about it. Next, please. So the Earth has a mineral dust cycle with many impacts throughout the Earth system. In the arid land regions of our planet, under conditions of strong winds, mineral dust is lofted from the surface or emitted from the surface. Where it interacts throughout the Earth system, it can absorb and or scatter radiation, so heat or cool the atmosphere. It plays a role in cloud formation. When it precipitates over the ocean, it's an important fertilizer for many biological processes. And when it precipitates over tropical forests, for example, it can be an important fertilization element. In addition, when it lands on snow, it plays a significant role in accelerating the melt of snow particularly in the mid-latitude regions. And of course, for us, it can be a hazard locally for breathing and for visibility. So it's involved throughout the Earth system. Currently, knowledge of the dust source mineral composition is very poor. And we need to improve that to understand better understand the current impacts of mineral dust in this cycle and its potential future impacts. Next, please. So we're going to use with EMIT, NASA invented technology called imaging spectroscopy, where we measure a spectrum for every point in an image. And this is depicted here with a line moving across the surface of the Earth through a telescope into a spectrometer onto a detector array. And then for each column in that detector array, we measure the spectrum or the fingerprint of the surface of the Earth. In this case, I'm showing the 10 important mineral spectral signatures that we want to understand as they relate to the mineral dust cycle and particularly radiative forcing. But you can see those lines from 400 to 2500 nanometers are all different from each other. So those are the spectral signatures of different minerals based on their molecular compounds. So we can actually see those fingerprints from orbit, and will be launched to the International Space Station. With those fingerprints, we can calibrate them, and then we can produce these detailed mineral maps of the Earth's surface. And this is the instrument we're building and we'll be launching in 2022. Interesting, the first imaging spectrometer was built by NASA a number of years ago, and I've shown just a picture for reference there. Next. So I'm very excited to report, well, it's been challenging building an instrument with COVID. None of us expected to have to do that. And there's a lot of hands-on work in doing that. We're very far along. We built a very much state-of-the-art instrument, optically fast, f1.8, to convey those photons, give us high signal noise, high accuracy of the minerals. I'm showing the optical bench that's now been assembled and been through launch simulation, and it was very well aligned. In fact, it's exceptionally well aligned, better than any previous spectrometer that I'm aware of. The electronics are ready. We're going to bring those pieces together onto the platform that's mounted to the ISS, shown in the lower left there. Telescope on top, electronics, it's sort of a sandwich, and then the platform that's mounted to the International Space Station on the bottom. And so we're very far along and expect to complete this instrument in February and launch on the 1st of May, 2022. Next, please. Our destination is the International Space Station. It has an ideal orbit. It goes over the air-land regions of the Earth multiple times over the course of a year. So we'll get multiple samples to see the surface, avoid issues if there are clouds, though mostly we're working in air-land regions, and or if there are severe dust clouds, we want to see the surface for our science. And as I said, we're planned to launch on SpaceX Crew Resupply number 25. And I want to mention that all the measurements from EMIT will be available to the public at the Land Processes Archive. Next. So this is a summary. Again, EMIT is focused to close our gap in understanding of mineral dust heating or cooling of the Earth now and in the future. Those are our science objectives. We're looking at mineral dust in the source regions to understand how that mineral dust, when it's lofted into the atmosphere, interacts with the Earth system. I'm showing in the center here the regions we will measure, which are the air-land regions of planet Earth, which fall very nicely below the ISS. Then we're using very advanced imaging spectroscopy to measure full spectral signatures of the surface of the Earth. And we'll do this for the air-land regions of the Earth, and we'll go from a situation now where there are about 5,000 measurements constraining Earth system models to 1 billion direct measurements made by EMIT. That's a very nice improvement. We will be using these measurements in conjunction with very advanced Earth system models that can take those initialized conditions of the surface mineralogy and project how they're interacting with their system today and how they may interact in the future under various climate scenarios, and those relate to our 2 science objectives. I did want to also highlight there will be additional value from the spectra that we will measure for geology and resources, biodiversity and ecosystems, agriculture, fire fuels, hazards, surface plastics, mid-latitude snow and ice impacts, algal blooms, and even methane and CO2. All these molecules or molecules related with these elements are captured in the EMIT spectral range. While we're focused on our science objectives and we'll achieve those, we hope our data sets can support NASA and others to investigate these other areas of research and applications. And as Karen said, for actionable information. So thank you very much.
Good afternoon. I'm Satya Kaluri. I'm the program scientist for the NOAA Joint Polar Satellite System. JPSS is celebrating 10 years of its first risk reduction satellite, SWOMI and PP. SWOMI and PP heralded new measurements in LEO orbit for NOAA. This includes the VIIRS image that has a day-night band. It has infrared channels that are designed to measure very high temperatures, like you see at the bottom left panel. The VIIRS temperature measurements are used to measure fire radiative power, which measures emissions from forest fires in California. I can see aerosols and dust and smoke traveling across the continental US. It has the advanced microwave sounder, or ATMS, and it also has the ozone sounder called ARMS, as well as an infrared sounder. And these four sensors together on SWOMI and PP heralded new observations to NOAA. Next slide. While SWOMI and PP is celebrating 10 years this year, NOAA 20 that was launched after SWOMI and PP continues to perform flawlessly in orbit. And in 2022, we plan to launch the next satellite, JPSS-2, followed by JPSS-3
So you go
and
ahead and
4.
open your mic and start your presentation when you're ready.
Next slide, please. And what you're seeing here is the JPSS-2 satellites that's fully integrated, undergoing test, and ready to launch in September 2022. Thank you.
Hi, I'm Li Luen Fu from the Jet Propulsion Laboratory of Caltech. I'm the project scientist for the Surface Water and Ocean Topography mission, or SWOT. It's a great pleasure to speak to you about SWOT. Next, please. What is SWOT? SWOT is a Pathfinder mission using new technology to address transformative questions on weather and climate change and its impact on our environment, in particular the ocean and the surface water on land. What makes it unique is the next generation radar altimeter to measure the elevation of water surface in 2 dimensions with a spatial resolution 1,000 times higher than that of a conventional altimeter. The footprint of a conventional altimeter is the size of 1,000 acres, whereas the footprint of SWOT is only 1 acre, the size of the lot of a large house. For example, only lakes of the size of Lake Tahoe can be resolved by a conventional altimeter, but SWOT can resolve a small pond, as shown by the aerial photo. Next. This animation shows the flight of SWOT over the Gulf approaching Florida, revealing the elevation change across the loop current, the waters of the Everglades, Lake Okeechobee, before it back to the ocean, pick up the edge of the Gulf Stream. So the technology is radar interferometry. The satellite will carry 2 radar antennas separated by a 10-meter mast. The radar antennas look sideways from the nadir, allow the determination of both the range and direction of signals for computing the surface elevation over 100 kilometer swath. So it produces a 2-dimensional map of water elevation instead of a 1-dimensional profiles by conventional altimeters. Next, please. SWOT measurements will address 2 key elements of the Earth system in relation to weather and climate: the energy and the water cycles. Ocean currents transport heat and carbon dioxide from the atmosphere to the deep ocean for long-term storage. If not for the ocean, the temperature at the Earth's surface would be a scorching 67 degrees Celsius. The CO2 concentration in the atmosphere would be twice as much. So it's critically important to assess the capacity of the ocean to continue absorbing heat and carbon. Climate change impacts freshwater supplies. Global warming is accelerating the rate of water cycle by increasing the atmosphere's humidity. The much more rapid precipitation and evaporation of water makes it difficult to assess the freshwater budget So SWOT data would be used to make this critical assessment of freshwater availability. Next, please. SWOT will also make unique observations of coastal oceans, estuaries, and river deltas with important societal benefits. About 10% of the global population is in the coastal low-lying cities threatened by sea level rise. Coastal cities are responsible for 20% of the world economy. Storm surges are encroaching heavily populated areas because of sea level rise, as this photo shows the flooding of the lower Manhattan by Hurricane Sandy. We need SWOT high-resolution measurements for improving storm surge models. Next. Estuaries and river deltas are places where river meets the ocean. They are most vulnerable to climate change, causing saltwater intrusion, river diversion, and the landform change. High-resolution measurements by SWOT will improve the understanding and the modeling of the waters in estuaries and the river delta, hosting 5% of water population. This photo shows the complex water surface of the river mouth of Mississippi, just south of New Orleans. Next, please. The status of the mission. SWOT is a joint mission of NASA with the French Space Agency, CNES, with the contributions from the Canadian Space Agency and the UK Space Agency. The payload module of SWOT has been completed by JPL. It's now being integrated with the satellite bus in France. The full observatory will be transported back to the US for launch at the Vandenberg Air Force Base in California by a SpaceX Falcon 9 rocket in November next year. The international science and application teams around the world are ready for this exciting mission. Thank you.
Right, thank you to our panelists. We're going to now move to the Q&A section of the program. My name is Liza Lester from EGU Media Relations, and I'll be reading you the questions as a reminder to our reporters online. If you have a question, please pop it into the Q&A and include your name and your affiliation. And if you want to ask it live, we will invite you to open your mic. So the first question is for Dr. Blackwell. It's from Irene Kotz at Aviation Week and Space Technology. She asks, where will Tropics launch from?
Well, the answer to that is we don't know yet. So the 3 launches for Tropics that Astrospace will be performing next year fall outside the PI managed cost cap. So the launch is being managed by the Launch Services Program at NASA Kennedy. So I expect that they will be announcing some of those details in the near future.
Thank you. And from Alexander Witzy at Nature, also for William Blackwell, will Tropics data be used operational and near real time as hurricanes approach landfall? And if so, how? And if not, why not?
Right, so Tropics was proposed as a research mission for NASA. So we don't have any formal requirements to do near real time broadcast. However, having said that, NOAA is of course very interested in using the data in real time to improve forecasting. So this is a good example of a NASA-NOAA partnership to bridge the gap from research to operations. So NOAA has provided some funding for us to look at the Pathfinder data and see how we might improve the latency so that data could be used operationally by the National Hurricane Center, for example, to do near real-time forecasting with that. And what we hope will happen is that what we learn from that experience can be translated to the Constellation mission, and hopefully somehow that we can add a near real-time component to the Constellation mission.
Right, and a follow-up question from Alex at Nature for Dr. St. Germain. A lot of these EVI missions have taken a long time to develop. Earlier today, we heard about Tempo and EVI-1, still on the verge of launch. How will you accelerate the time between Earth-sized missions being recommended or selected and actually being flown?
Yeah, that's a good question.
There we go. Sorry, was stuck on mute. So it's a great question, and the Earth Venture instruments were the Earth Venture Instrument Program came out of the 2007 Decadal Survey, and of course at that time the market for host capability, hosting capability, and it was very different. Since then, of course, there have been real changes in the commercial hosting market, and of course, almost a revolution in new space. So we've gone back to the National Academy and actually about a year ago and or a little less, and asked them this same question. We're going to take a look at the whole EVI and Earth Venture program, and really do a deep assessment on asking the question, are there adjustments we should make given how much has changed since the program was first started, particularly in the hosting market. So I expect the Academy to come forward or sometime in the spring, I think, with that analysis and report, and then we'll be looking at making some adjustments, because we see the same challenge. We would really like to get these capabilities to orbit much faster than we've been able to. Thanks for the question.
Do we have any additional questions from our reporters in the audience? Going once, going twice? Further questions? All right, well, then with that, I would like to thank all of our panelists for these great presentations. If you have further questions for them, be sure to follow up with them or with their PIOs at NASA. And I'm turn it back over to my colleague Becca for final comments.
Yeah, thanks again, everybody who joined us. And I'll just note that our next press event today is a media roundtable at 3 p.m. Central on using dogs to sniff out oil spills. And I have been told that there are videos of dogs doing jobs, so that's just a plug for that event. And with that, we'll wrap up this press briefing. Thanks again to the panelists for their time.
Thank you.
Thank you.